Today we are going to generate music from chickens. The algorithm in this max patch takes a video and extracts motion and movement from it. It furthermore turns it into usable data for generating melodies, chords, and musical note events. This is a very simple algorithm, but it leads to surprisingly cool and interactive results. So let's build this from scratch. Okay, the first thing I'm going to do is to get a video file in my empty Max MSP patch, and then I'm going to start thinking about how exactly I can implement motion or movement detection on the basis of that video. So what I'm going to do first is to go to the video tab here, the videos tab, apologies, and then choose one of the built-in video examples in Max MSP. So I'm going to choose chickens.mp4, my beloved, and I'm going to click and drag it into my Max MSP patch. Right, to visualize this, the video that's going to come out of this object, I'm going to create the jit.pwindow object, which looks like an empty box, but what it's actually going to do is that it is going to visualize the incoming jitter matrices sent out from this jit.playlist object. Let's also type in the name of this object as well. There we go. So if I play this now, and if I set it to loop, I can see my chickens in jit.pwindow. So far so good, pretty simple. But how does this play into motion detection? Well, we have to be aware of two things, right? So first of all, this is actually not movement. This is actually not a real video. And what I'm trying to say by this is that, as you might know, this is just a bunch of images, right? This is how videos work on digital media or digital systems. It's just a collection of frames of images that are presented at a consistent rate, one after the other. And if these images are sequential or if they are congruent in some way, our brains just put it together and they say, well, it looks like a chicken. It's really cool. I'm going to use this video from here on in all of my YouTube tutorial videos for Max MSP and jitter. Or your brain might say something else, but the point is we realize that this is some kind of video or some kind of moving image, even though we do intellectually know that this is an illusion. All right, now why is this important? Because if we are thinking of motion detection, what we are actually looking for is the difference of the position of something. And let's imagine this message box with chicken in it is the something. What we are looking for is a difference of the position of something from between one moment and the next, right? So if at one moment I'm here and if another moment I'm there, then there has been some motion. It has changed places. And I can find the difference between the places or the positions of my thing between these two moments, and that would give me a simplistic interpretation of motion or movement. And similarly, if I go from one step to the next and there has literally been no movement, then there is no motion. And I either get a value of 0 or I get nothing, and then I will be done with that specific step. So this is all to say, to detect motion in videos, I want to take each step, in this case each frame, and see what has been displaced compared to the previous step, as in the previous frame. Right, so in this case, I'm not looking at chickens and their positions, but I am looking at pixels. Let me write that down, pixels and their values. So I'm looking for differences in the values of the pixels, of the colors of these pixels between each step. And as we probably already know, pixels are represented in the RGB color space, and in an ideal normalized world, this means that each pixel has 3 values that go from 0 to 1. Right, so like this much red and this much blue, this much red and this much green, and all the possible blue because the highest value is 1, and this would be the color of one pixel, this much red, this much green, and this much blue combined, and so on, repeat until infinity, or until we have all of our pixels defined as a specific color. Right, so again, I want to look at the differences between the pixels, the pixels from one step to the next. And what that concretely means, if we have to kind of come up with an equation for this, is that what I'm going to describe as motion is going to be the current pixel, right? So whatever pixel value I have right now minus previous pixel. right? So I'm going to subtract the values of the previous pixel from the current pixel. And guess what is going to happen? If there is no change, if there is no difference from one frame to the next, well, these two are going to be the same, right? It's just going to be the same pixel value, so I'm going to get 0. But if the current pixel deviates from the previous pixel, if it's a bit brighter, if it's a bit darker, if it's a bit more red, if it's a bit more green, whatever, then I'm going to get a non-zero value, which is then going to represent motion in my algorithm. All right, that's enough talky talk. Now let's actually put things into practice, right? And how are we going to implement this exactly? Well, first we have to figure out subtraction, which is pretty easy. I just need an object called jit.minus. That's just a subtraction object. It's going to subtract one matrix from the other. And I believe if I just simply do this, I'm just going to get a blank screen. Yeah, because I'm subtracting this matrix from the exact same matrix, and if you subtract something from itself, you get 0. Right? But what jit.minus does is slightly cooler than that. It actually goes pixel by pixel. So for each pixel or cell in the incoming matrix to the first inlet, it is going to find the corresponding cell in the second matrix going into the second inlet, and it's going to subtract that from the cell value or the pixel value of the first matrix, right? So this can be the basis for our simple naive algorithm. Now I just need to find a way to how to get the previous pixel value or the previous matrix value. We can also write it like this, right? Motion equals current matrix minus previous matrix. Maybe that's a better way of writing this. There we go. Motion is current matrix minus previous matrix. So how do we get the matrix of the previous frame, the image of the previous frame? How can we get that? Like if we could use a delay object, if we could delay the video by one frame, that would be cool. But I think there is a slightly easier way of doing that, which is called, not JIT, it's called TLL. So an object that just has the letters T and L in it. And if you know what it does, then it's good. If you don't know what it does, it's really cryptic, right? So T, the object T, is short for trigger because it's going to trigger a specific set of operations in a specific order when it receives messages, right? The two L's means that I am sending you a list and first send that list out from the rightmost outlet. And once that is done, send the same list from the leftmost outlet. And for the purposes of this video, you can just treat jitter matrices as lists. There is more to that, but again, for the purposes of this video, it is not that important. What this is going to do is that it's going to let us send out this jitter matrix twice in a very specific order. And this is the order I want. There we go. So we are going to cross the beams. We are going to cross the same matrix. We are first going to send it to the first inlet, and then we are going to send the same matrix to the second inlet. And this is a bit of a puzzle, right? You need to be familiar with the order of messages or operations in Max MSP to kind of figure this one out. But let's just think about this. So we know that in Max MSP, things go from right to left, right? So first the right thing gets processed, and then the left thing is going to happen. So what is going to happen if I send this jitter matrix here? If I send a single frame of this video into this object? Well, first, the rightmost outlet is going to send it to the inlet of jit.minus, right? And this is going to trigger the operation. Then it's going to take whatever has been sent to the second inlet previously, and it's going to subtract that from the jitter matrix I have just sent into it, and it's going to send out the resulting matrix. Right after that, it is going to send out or current matrix once again, but this time it will send it to the second inlet of this jit.minus object. And what that is going to do is it's just going to set the operation. It's not going to trigger anything, it's just going to set the matrix that this object is going to use once the process is triggered again. And then next frame, the frame comes, is triggered, and it is and the previous frame is subtracted from this frame, and then this frame is sent to the second inlet, becoming the previous frame. It's a bit confusing, but if you go over the data flow in your head, it's eventually going to click. But what is cooler than this very seemingly simple but actually complex algorithm is what's going to appear if I create a jit.p window. Now check this out. we have motion detection. We are looking at our beautiful, lovely chickens, and we are only seeing the chickens in the output of JIT.minus because they are the only things that are changing. They are the only things that are moving, right? So we are kind of filtering the video based on motion detection, and technically we could do this with any video. We could do this, apologies, with live input. Yeah, I'm getting too excited because motion detection is really, really cool. But this is one way of isolating this information. But now we can actually play around with this, right? And there are a few things we can do to this. And first of which is to not think in terms of colors, but to actually convert this video to black and white and then do the motion detection. Now, this is an optional step, right? If you want to use this video or use this resulting images as visual material, these chickens are perfectly fine. But if I want to eventually extract values from this jitter matrix, then I have to be careful because I want a single value per pixel. And now I am in a color space where there are 3 values, red, green, and blue. So if I want to eventually get this motion information as data, an important first step I can do is to put the video through the object jit.rgb to Luma. And that's going to convert the video into monochrome, meaning that each pixel is just going to have a single value. See, it's just going to be between 0 and 1. 0 is black, white is 1, and then anything in between is anything in between. And then we get this nice monochrome image in our hands instead of the colorful image. And after that, I can simply do whatever I want, right? Actually, I can just take the output of this jit.pwindow object. It's just going to send the exact matrix that it receives. So I can just take my difference algorithm, plug it here, and check out the result. And if I compare it with my regular chickens, I will also see that it's pretty much the same. It's just that this is black and white, meaning that each pixel has a single value associated with it. All right, and another cool trick I can do is to make this motion leave trails, right? So right now, if the motion is happening for 1 frame, it appears, and if there's no motion in the frame that follows that, then there is simply nothing. And if we could smear this motion a bit, then I think it would look a bit cooler. It would be a bit more representative of long time movement instead of simply the difference between the previous frame and the next one. And I can achieve this by using the object jit.slide. Right, cell-wise temporal envelope follower is the description for this object. It's a bit too cryptic for my taste, if I'm being honest. What this does is that it's going to kind of blur the image either as the values are going up or as the values are going down. And I want to blur the image as the values are going down, so I'm going to use the attribute slide_down and give it a value like 10. Right, so what is going to happen if I just plug this in here? Look at this. Now our motion detected chickens are leaving these cool trails, right? And if I, let's say, make a message box that says slide_down $1, put it here, make a float number box, and I can in real time change the smear amount. So if I really want to leave these trails as the image is changing, maybe like make this cool video sculpture out of things, I can have a lot of slide down, or if I just simply want the difference from 1 frame to the next, I can simply use slide_down set to 0. Right, and I think 10 is a cool number. It's my favorite number, 5 times 2, so I'm going to use 10 here instead. Okay, so this is visual motion detection, right? So if you just want to create cool videos, and if you want to take this motion and use it as the basis for some video processing and you get some cool results, great. But I like audiovisual stuff, and I like to create music and sounds from interesting visual information and vice versa. So what I would love to do here is to take this information, whatever's coming out of here, and use it to maybe control like a keyboard, just trigger a range of available keys based on how much motion there is. It's a bit vague in my head right now, but let's try to put it in practice. And if that is what I want to do, I want to have a certain amount of data. Right, right now this video is, I think, very high resolution, so we are going to have thousands upon thousands upon thousands of pixels. And let's say I want to work with a possible 100 data points. I just want this to be scaled down to 100 data points. And I can scale any jitter matrix down by creating a new jit.matrix, giving it the information that it needs. So how many planes is this going to have? Well, this is just black and white, so one plane. What is the data type? Float 32. Values go from 0 to 1. And what is the dimensions of my matrix? Well, let's make it 10 by 10. Now, what does this mean? Well, now if my video goes into this jit.matrix, it kind of gets downsampled. It kind of gets downscaled in order to fit a 10 by 10 grid, right? So it's like I'm just turning the resolution from like 1920 to 1080 to 10 by 10 because I just traveled back in time and now I'm in the 60s or 70s or something when they had these really low resolution monitors, and it's how I want to see it. This, by the way, is also a really cool trick for downsampling videos or images in your Max MSP jitter environment. Okay, but since I have this, now I can kind of treat this as a database, right? So eventually maybe all like movements here above a threshold can trigger a node. I think that would be really cool. And if I'm going to do that, maybe it's a nice idea to not treat this as a screen, but kind of unroll it into a single strip, into a single row instead of this 10 by 10 grids. And one way of doing this is to use the jit.scanWrap object, which is going to kind of do what I've just described, honestly. It's just going to take the incoming matrix and it's going to make it fit the specifications of the matrix I give to this object. I give to jit.scanWrap, and it is going to unroll that matrix, and there we go. Now we have a jitter matrix where we have 100 cells or 100 pixels, and it's essentially just these rows added one after the other on the ends, right? So this is an unrolled version of this. Okay, that is nice. Now, what I want to do is to isolate the pixels here that are above a certain threshold. And I can do this by simply checking if they are above the threshold and then sending 1 if they are and sending 0 if they are not. And this is really easy to do using jit.largerthan. Right, I can give the comparison value to jit.largerthan not as an argument. This is not like the other Max MSP objects, but by giving it the attribute val. So let's give it val 0.21. Right, so if the pixel is larger than 0.21, give me like a just completely bright pixel. But if it's not larger than that threshold, do not give me anything. Right, so I hope you can see what is happening here. This is a really cool way of kind of filtering these jitter matrices containing information instead of visuals. Right, and I can't change this value in real time, but just sending a value into the second inlet, right? So I can connect a floating number box and I can type in 0.5 and then I'm probably not going to get anything, or I can type 0.1 whereas I'm going to get a lot of stuff. I can type in 0 and then just everything is going to be let through. Right, so I like 0.50. Maybe that's a nice starting point, and then we can experiment with different threshold values here. But now that we have this unrolled matrix, and by the way, I just want to realize here how cool it is that we are taking this video and we are doing all of these operations on it to kind of boil it down into data, right? So this is also the chickens, but we have done so many stuff to these consecutive images of chickens that what we are left with is a bunch of cells where each cell represents how much movement there is in that area corresponding our chicken video. I think that idea of just taking something that's intended to be a video and image and just manipulating it into something that represents something completely different is really, really cool. But okay, I digress. So let's now turn this jitter matrix into something that actually makes sense for us, and let's use jit.iter. And what is jit.iter is going to do? Well, it's going to one by one send out the contents of a matrix, so cell by cell or pixel by pixel, from its leftmost outlet. The right, so the second outlet, or the right outlet to the right, is also important because this is going to give us the coordinates of each corresponding pixel, right? So it's going to be pixel number 0, this value, pixel number 1, this value, pixel number 2, that value, pixel number 4, this value, and so on, and so on, and so on. And this is going to play into our algorithm for playing these out as some kind of soundscape or a musical figure. So I know that the pixel number comes out of here, and for now, let's just treat these as MIDI numbers, right? So there's some kind of a conversion happening, a mapping happening. The pixel index numbers become MIDI note values, right? So this is the point at which we are going to turn the visual information into sound information. But I know that some of these pixels are going to have the value of 0, so I only want to let through ones that are not 0. And here's how I would do this. I would create the object int. And int is a placeholder. It's just going to contain an integer number, and then you can send that integer number out when you want to by just sending a bang to the first inlet of int. And for each step, for each pixel, let's do this. Let's first get the coordinates and send that to the second inlet of int, loading it into int, but not sending it out yet. And then let's follow this up by checking the value of the pixel that comes out from the leftmost outlet. And let's simply do cell 1. And what is cell 1 going to do? Well, if the pixel sends 0, it's not going to do anything. But if the pixel value is 1, so if the value of 1 is sent out from here, cell is going to say, now wait a minute, that matches my argument, 1, so I'm going to send a bang from here. Right? And if I then send that bang to the int object, it is simply going to send out only the index numbers of the pixels that do not have the value 0, that are not black, that do not contain the value 0. And we can kind of validate this, right, by using the print object and just printing the results. And if you look at all the numbers here, and if you have a 20,000 IQ brain, you will probably match the pixels here to the index numbers here. Right, but this is going to be the pixel index numbers that pass the test. Meaning now I can simply, I don't know, create a make note object, right, to trigger a MIDI event, give it a velocity, give it a duration, let's make it 500 milliseconds. No, let's make it 1 second. And this is very important for what we are doing. Let's give it the attribute repeat mode 4. Now, why am I doing this? Why am I giving it this strange arcane attribute? Well, that is because I'm going to be receiving these pixels like 30 times per second or 60 times per second. And it could be that while a motion is detected in one of these pixels, it keeps being detected in each successive frame. And if it keeps being detected in each successive frame, it's just going to send out the same node over and over and over and over again from this int. And normally, without this attribute, make note is just going to mash that key on its imaginary MIDI piano. So to filter out those kind of repetitions, we are giving it the attribute repeat mode 4, making it ignore note repetitions until that specific note has been played. All right, and finally, we have our note out. So the output of make note goes into note out, and let's try this. Let us do the final connection and see what we get. Amazing. Beautiful even. Let's stop the video so we are not bombarded by all these MIDI notes. Now this sounds a bit random, and this is essentially the starting point of your creativity, right? So if you pick something up here and you like generate scale notes using MIDI, or you generate notes of a sequence using this instead of all possible notes between 0 and 100, that would be one way of cleaning this out and making it a bit more musically pleasing. But I will do a little trick to make it more musically pleasing, which is going to be to scale these note numbers, which normally go from 0 to 100. It's actually 0 to 99, but I'm imagining they go from 0 to 100 to a smaller range, such as, let's say, 25 to 77, or no, 25 to 66. And now if I play my video, well, let's get our chickens here as well. Now I should get something a bit more listenable. I can also filter the incoming motion matrix a bit more strongly to make sure there are less note events happening. Maybe 0.35. There we go. Or if I want really strict hardcore filtering, I can also use 0.5 as my filtering value, so only the very strong motion is going to be registered. But there you go. And if I lower this, I'm just going to get this beautiful cacophony of chickens. And there you have it. We have performed motion detection. We have actually manipulated and wrangled that information into a form that is useful to us audio-visually. And we have then implemented a very simple algorithm to just trigger a bunch of cool MIDI notes automated in reaction to the movement inherent in the video itself. And this could be taken to a lot of places as always, right? So this again can be the starting point for your creativity. Consider the MIDI numbers here. Think if you can trigger samples or a specific collection of MIDI notes or anything else that you can think of. And maybe it's also interesting to consider the specific values in these pixels. Right now we are just using 1 or 0, but maybe the more motion there is, the stronger the note is, and the less motion there is, the more quiet the note is, or maybe it has some kind of filtering like effect, the motion. I don't know. It's just that you can do so much with these values as well. But I will leave that to you for now, and I hope you have a lot of fun with this, and as always, thank you for watching.